All right, good morning, kids. Let's kind of go over some stuff to get you ready for the test on rate laws, which will be Tuesday, tomorrow. I will send that out about 9 o'clock, and that will be due back to me by 3, so that's going to give you 6 hours to get done with the test. Okay, so let's say we have kind of the big picture idea. Make sure that you know the zero order, first order, and second order, okay? If there's any like real specific equations that you need for half-life and stuff like that, I will give those to you. But you just, what I promise you now, what I want to emphasize most is the first order and second order. So that's going to be huge. Make sure that you remember first order is the one that involves natural log. Second order is the one that involves the inverse of these, okay? I just remember first order looks like an L, okay, that's natural log. What I will do, and then also remember written like this, where you have like the natural log of A equals negative KT plus the natural log of A naught. Okay, remember that's the integrated rate law. If I ask for just the rate law itself, that would just be like R equals K times the concentration of A or whatever that is, okay? So make sure that you know the difference between the rate law and the integrated rate law. Make sure that you can do that process with like that iodine lab where you go through and you keep like the concentrations the same and you divide that by the different rates, okay? Where you get one of these to like cancel out, and then you can figure out what the order of magnitude is, whether that's zero order, first order, second order, okay? Make sure that you can do that. On the review I've sent out, that I'm going to send out, there's some equations. Don't spend a whole lot of time on that. Those are just kind of general basic knowledge kind of things. If there might be maybe one of those, okay, so and it won't be anything complex, okay? The majority of the test is going to be over this rate law stuff, so let me kind of give you an example of this whole idea. Let's review and go back to like Kc and Kp, this whole idea of equilibrium. So let's say that I gave you this reaction where you have N2O4 turning into NO plus NO3, and this is going to be important. Everything here is a gas. And so let's say that we've measured the pressure of just the N2O4 before we start, and that's 1.2 atmospheres. Okay, again, to kind of give you some perspective, you're probably in your house right now under an atmospheric pressure of about 1 atmosphere. So this is a little bit more than 1.2. So it's a little bit more than normal, but not bad. And let's say that we'll make it simple, and let's say that the tank has a volume of 1 liter. So what's going to happen is that this reaction is going to go in this direction. And when we get done, and this system reaches a point of equilibrium, that we measured the pressure again after equilibrium, and this is going to be important. After it reaches equilibrium, the pressure has gone up to 1.8 atmospheres, okay? So when you look at what's creating this pressure initially, it was just the N2O4 molecules that were bouncing around. So as these shifted and you began to form NO and NO3, then that means that that pressure now is also created by these little particles bouncing around as well. So oddly enough, we're going to kind of look at this from like a chart involving equilibrium. So we're going to start off, we're going to go, oh, okay, that's N2O4. Okay, can reach a point of equilibrium where you have NO and NO3. Okay, this isn't like a nitrate ion. This is nitrogen trioxide. And we said that initially was 1.2 atmospheres. And we're going to assume that there was no NO and there was no NO3. And so here's your rice chart, oddly enough. And some of this is going to be lost. And we're going to add it over here, and we're going to add that over here. So when we reach a point of equilibrium, this is 1.2 minus x, and this x is going to be significant. We have to keep track of that. And that's going to be x, and that's going to be x. So we know that this total pressure of 1.8 atmospheres up here has to be created by the sum total of the pressure created by the N2O4, the NO, and the NO3. So all of these are combining to produce that pressure of 1.8 atmospheres. So what we're going to do is we're going to add these together. So we're going to go, okay, 1.2 minus x, which is the concentration of my N2O4, or my pressure of my N2O4 at that point, plus x, which is the concentration of my NO, plus another x, which is the concentration of my NO3. All of those together are going to add up to equal 1.8 atmospheres. Okay, that's kind of punchy. Now, conveniently, I got minus x and plus x, so that just drops out. So I have 1.2 plus x equals 1.8. So check my math, but x is going to equal 0.6. Now, so if I take and put these numbers back in here, and I take 0.6, 0.6, okay, 0.6, 0.6, and 1.2 minus 0.6, that gives me the pressures created by each one at equilibrium. Now, if I want to calculate Kp, which I can, remember that's going to be products over reactants because it's a gas and we're dealing with pressures. So that's going to be NO times NO3 divided by the pressure of my N2O4, right? So in that case, that's going to be 0.6 times 0.6 divided by 0.6. And this 0.6 here comes from that 1.2 minus x. So these are going to drop out. My Kp value is going to be 0.6. So what this means is that this is when Mother Nature reaches a point of equilibrium, this is this numeric value is 0.6. Now, remember, if I go through and I calculate like a Q value, and it's bigger than Kp, look at how that's going to shift. If Q is less than K, how that's going to shift things. So that's something else that you might want to look at. Now, then what we could do is we could come in here and say, okay, let's have a little, let's say that this is the rate of the reverse, okay, rate, or we could talk about the forward rate. And at equilibrium, that rate is going to remain constant, whatever that is. And at this point, we're going to inject some NO, not NO, but nitrogen monoxide into the system. So because we're injecting NO, which is a product, what that's going to do is that when we inject that NO in there, which is a product, that's going to spike that reverse rate. Because now Mother Nature is going to flip out and go, oh my God, we have too much product in here. We're going to spike that reverse rate. Now, what's going to happen eventually is that this thing is going to level back off at a new equilibrium point. Okay, so we're humming along, we inject some NO, and once I get over to school, I'll show you another demo how you can play that out using chemicals and heat. All right, make sure that you can understand these energy, that was horrible, diagrams where you have energy here and the reaction proceeding like this, okay? And so let's say that you might get, I don't know, something like this, and be able to tell me, okay, what's going on with this? So remember, this first part here is going to be your first activation energy. And so this is A turning overall, A turning into C. So we end up with C here. So what's going to happen is that this is going to be this first activation energy, okay? And then you're going to have some type of transition state. And then you're going to form an intermediate of B. And then B is going to have this big activation energy. And then you're going to have a second transition state up here. And then you're going to form C. Now, overall, this is going to be a slightly endothermic reaction because C actually ends up with a little bit more energy than what we started with A. If we end up down here, below A, that's going to be an exothermic reaction. So it's exo here, endo here. Now, one of the things you want to look at is which one would be the fast step and which one would be the slow step. So this one, because it has the slowest or has the lowest activation energy, is going to be the fastest up. Because at a certain temperature, that means more collisions are going to be able to cross that threshold of that activation energy than what's going to happen over here. So this would be your fast step, and that would be your slow step, okay? I've sent out the reviews. I've sent out the answer keys to those. Those are really big things. I'm going to film a demo this afternoon, assuming that I can get into school, and I'll add that to that, and we're also going to have this conference call at 11:30. So anyway, I just needed to explain some things here where you could look at some diagrams and how they play out. So, all right, well, I will see you all in about an hour.